It's our pleasure to have Yoel Groman. He's going to speak once about relative SH and mirror construct.
Okay, thanks, Umut, and thanks for inviting me to this conference. It's a great pleasure to visit here and be here. Okay, so the title of the talk is relative SH and mirror construction. So I would like to describe some kind of program. So the way the talk is structured is I'm going to spend like 20 minutes talking about some kind of big picture, and then the rest will be actual mathematics. So if you get lost in the first 20 minutes, don't worry, we'll get back to Earth. Okay, so the problem I want to talk about is the reconstruction problem. So, already. So the reconstruction problem in mirror symmetry is about, so basically it says, what is this problem? So given a weak SYZ fibration, produce the mirror. Now, so actually, I put the word weak in quotation marks because actually, so you probably heard that those of you who were in the conference, in the kind of the summer school last week, in the workshop, so you heard from Mark already that kind of initially there was some kind of clear definition of what an SYZ fibration should be, but then people realized that it doesn't exist when you define something strictly with special Lagrangians. So actually, one can kind of weaken the definition and still do a lot, but it's still not completely settled what is exactly the right notion, like how weak, so I'm leaving this as something which is still open, and it kind of this requires input kind of Euler theory. But still, we know one when we see one. So in a lot of cases, you can just say, here's an SYZ fibration. Let's what is the mirror? And when we ask, like, what is the mirror? This can be thought of in a number of different ways. Like, basically, one can ask for the manifold we produce to satisfy some version of mirror symmetry, maybe homological mirror symmetry, or Hodge theoretic mirror symmetry, or whatever. And there's also some way, but I don't want to go into, kind of there's a rigorous way of formulating what it means for something to be the mirror. At least when I think of it, I think in terms of like where anyone who's familiar with this. So Kontsevich-Soibelman formulated something called the lifting problem. So basically that's what I'm kind of, an SYZ fibration gives rise to some kind of Kontsevich-Soibelman lifting problem, and we want to solve that. Okay, so now, so there's a number of approaches which already exist in the literature. So I just want to very briefly kind of compare. So of course we have kind of so existing approaches. So there is the Kontsevich-Soibelman, which and very similar, which kind of 3, and then maybe something called the old Ross-Sievert program for toric degenerations. They kind of, to some extent, they cut out the symplectic geometry. They reason what kind of thing should the mirror be, and in the end, you don't need any kind of so you get some kind of a solution to the reconstruction problem. Now, but we kind of have a different aim than what they have, because we want something which we can kind of relate to symplectic geometry easily. So Okay, so that's one approach, and then another approach is family Fleur theory, which a number of authors have written about, and this is kind of this is where we're in direct competition with family Fleur theory, and basically the place we're trying to improve is kind of in treating singularities. So this family Fleur theory works in a limited way when you have singularities. We kind of claim that relative SH is kind of a better way. Okay, so that's just some just some generalities. Now, okay, so what is this relative symplectic homology program? So first, let me I have to say, like, what is relative SH? So first, what type of mathematical object is this thing? So given so if you have a symplectic manifold, and inside the symplectic manifold you have a compact set, just a compact set, nothing else. Then to this we can associate something which we will denote by SH star sub M of K. So it's kind of the symplectic homology of the compact set K relative to M. And this, which is, what kind of object is it? So first it's kind of a Banach PV algebra over the Novikov ring, over the Novikov field. So Banach means it's kind of it has a norm. So this norm is a very important part of the structure. So it has a norm. It's complete with respect to this norm. Algebra means it has a product. BV maybe is a little less familiar. It's some structure which I will just kind of describe concretely in an example rather than say what it is. So this is some kind of thing which we can associate to any compact set, and given an inclusion of compact sets, we have a morphism in the reverse direction. So we have a morphism of a map of BV algebras from the bigger set to the smaller set. Okay, so that's something we can associate. And what I will do is I will first kind of describe basically the so yeah, what is the kind of, how do you define it? Very briefly, what is kind of the most important case, and how it relates to other notions of symplectic homology, which you may be familiar with. So yeah, any questions so far? Okay, I have what? Did I say? Yeah, it's a priori pre-sheaf. Yeah, it's a pre-sheaf. I don't remember saying this word, but in some cases it has. So yeah. Yeah. Yes. So okay. So the formal construction will be very brief, because if it's only kind of if you're kind of symplectic geometer and you're familiar with this kind of thing. So formal construction is just if HK consider H from time dependent Hamiltonians to R, such that H restricted to K is less than 0, then SH is defined to be the kind of some derived node in, but I will not say the word in the notation. So some derived inverse limit of over truncations of so when you have a Hamiltonian function, you can define its Floer homology, and then Floer homology is something you can truncate, meaning you can you only take into account curves which have energy less than or equal to lambda, and then you do a limit over all these Hamiltonians which are less than or equal to which are less than 0 on k, and then you take an inverse limit over all these possible truncations. So that's a formal definition, probably not very useful, but like we should think of this as the Floer homology of kind of the indicator function, where hk is the function which is defined to be 0 if x is inside, and infinity if x is outside. Okay, so that's okay. So that's the formal definition of this invariant, and by formal properties of Floer theory, you can see, for example, this thing like this continuation map is just whenever you have an inequality between Hamiltonians, you have a map over the Novikov ring in the reverse direction. Okay, so this is for people who are slightly familiar with Floer theory. Okay, now let me say, describe what this thing is in kind of an example, which is of central importance. So any questions so far?
So we should think of this as, can you hear me?
Yes, I can hear you.
So we should think of the periodic orbits to be close to the boundary of K, but K, never going outside.
Morally, yes. Morally, that in practice, when you have a compact set, you will have kind of critical points here. You'll have let's say this is K, and this is your function. And you basically you're trying to approximate it. You will basically be approximating it by an S-shaped function, something which is close to 0 on K. And
yeah, that's a picture in my mind, right? Yeah.
And you will get in practice, you get critical points here, you get periodic orbits here, you get additional periodic orbits here, and then you have critical points here. So there is some stuff going outside, but the point is that if the value is kind of big outside, then in some sense it suppresses the contribution. But yeah, making this precise is not so a non-trivial matter. But yes, you should think of it as basically things which have critical points here and Rabe orbits at the boundary.
On the technical level, is there any statement on what the generators are?
Yeah, I will say it let me. I'm getting to it. So okay. So maybe before giving an example, I'll say what is. So let me first. Yes, I will. Yeah. So first, I will say something general. So the general thing that I want to say is, how does this, people have already know, so kind of people who are familiar with the notion of symplectic homology. So what is the relation to ordinary symplectic homology first? So yes, so let's say if K is a Liouville domain. Note, and in general, K can be an arbitrary component. The Liouville domain, then K, first of all, it has a completion. K lives inside something which completes it, and one can talk about this same invariant that I defined. One can talk about symplectic homology of K relative to its completion. And then this thing is a certain completion of ordinary symplectic homology. And I will just remind what is ordinary symplectic homology. of just ordinary, meaning so the ordinary definition of SH is that you take, so you have this Liouville domain K, and then because it's like being a Liouville domain means it has contact boundary, and then so you have kind of on the boundary you have Reeb orbits, and then the kind of as a module, as a vector space, ordinary SH is kind of the homology of a complex which is generated by critical points inside and by Reeb orbits on this boundary. And then there is a differential which counts all kinds of curves which connect these Reeb orbits, and there's a product which counts kind of pairs of paths which connect. Okay, so that's ordinary SH, and I'm saying this is a completion, meaning we're allowing certain infinite sums. I will describe this in an example. So this is what we have when we have K relative to its own completion. And notice I drew all the curves. When you have kind of, in this setup, all the curves kind of stay inside the domain. So we added some completion, but it looks like it plays no role because all the curves stay inside. We'll see later it does play some kind of role. But, and then what if, so that's, now suppose we have an embedding of K inside some manifold M. So M now is not the completion of K. It's just some arbitrary, it could be a closed manifold, it could be an open manifold, but K is not kind of embedded as a Liouville subdomain. There's no exactness assumption. Then, so let's now kind of, I drew it as K bar, but let's now think of this as M. So this is some manifold. Then in addition so you have this ordinary SH, and then you get, morally at least, making this precise is not also a non-trivial matter, but you should think of it as a deformation. So you get additional curves which also go outside. And somehow these curves that go outside, they have higher energy in some sense. So you get, and also for the product, you have kind of curves go outside. So you get some kind of deformation of ordinary SH. So that's what you should think of. So in case where K is a Liouville domain embedded inside a manifold which is not necessarily a Liouville domain, you should think of it as a deformation of ordinary symplectic homology.
Can you say it again? So A is still like the white thing you drew.
K is the white thing here I drew.
And it's a Liouville domain.
It's a Liouville domain, but M is just some symplectic manifold, some arbitrary symplectic manifold. So you can't. There's no maximum principle which rules out curves going outside. But these curves, the effect, one wants to claim that their effect is kind of lower order. Also, it's a non-trivial statement. It's also non-trivial to kind of state this correctly. But this is what you should think of. So I hope this was a long answer, but does this answer your question, Bernd?
Yeah, totally. Sure.
Okay. Yes, and now I want to somehow, okay, so this was a description of kind of what this is, and then I want to say the most important example. So let me describe this in an example. So the most important example is the case of when you look at kind of sets inside the cotangent bundle of a torus. So let me just describe the answer. In that case, the answer is, so let's say you, so let's say M is the cotangent bundle of a torus, which we think of as Rn times Tn with coordinates. Here we have the P coordinate here. Case is just Rn, and we have some kind of projection. Okay, so now this is okay. This is our M, and then let's say we have some convex polytope inside Rn. And then K will be the pre-image of this thing, of this convex polytope. So draw it here. This is P inside R2, and we then the answer is that symplectic homology of K is basically you take the Novikov ring, you adjoin variables like invertible variables and invertible variables, which these will be the things which are in degree 0. And then you adjoin additional kind of dz1, dzn. These are like vector fields. These are all in degree 1. And you impose the relation that dzi squared equals 0. So and then you take a completion. So note, and I will describe what this completion is. So yes. Yes, like as commute, we consider them as, yes, these are like these commute and these anti-commute. I mean, but I guess this is what.
Like the multiplication of Zi and dzi.
So this should be the algebra of polyvector fields. So yes, so the Zi and the dzi commute. Yes. Now, so note, before I take the completion, this is kind of familiar. This is the familiar, so this is a particular instance of what I was describing here, because here I'm basically looking at this Liouville domain inside its completion. So really, as I said, you get, like, this is what is known as the ordinary symplectic cohomology, and this expresses the fact, like it's a well-known fact that somehow symplectic cohomology is the algebra of polyvector fields on the mirror, in case kind of when the mirror is kind of affine. And so this is really like the mirror of the cotangent bundle of the torus is really C star to the n, and this is the algebra of polyvector fields in C star to the n. So and then the completion, let me just describe. So the completion is basically, let's look at functions which kind of converge here. So let me, where's the eraser?
Like it's a computed problem, but the rate is a greater computed problem.
Yes, it's a greater computed problem. Yes.
And that relation is invoked only automatic.
You're saying, by just saying that it's a graded commutative, like this, yes, you're right. If I say this is degree 1, I just say graded commutative algebra, which is always, like symplectic homology is always a graded commutative. Yes, you're right. Okay, so the explicit description of the completion is just that we just have to define the norm. So the norm of Z to the I is basically it's E yeah, I kind of have to choose some kind of center point, or I arbitrarily choose some center point to describe this norm, and then each Reeb orbit has a place where it occurs. So like each, how should I could just say, well, I is I will be some multi-index. So I defines a line of some slope, and that line there is some kind of the kind of where it touches our convex. We're looking at a convex polytope, and then what we will just, and let's say if kind of the length somehow, let's call the vector which goes from between these 2 points x, that's going to be e to the ix. But what you should really think of is that z to the I defines some kind of function. We talked about last week, we talked about when we look at Rn, we can look at, we have kind of lambda star to the n. First, let me complete this, and then I will complete the sentence that I just started. Okay, so this is the norm of z to the I, and then the norm of zi, dzi. For each I it's 1. And what this really is, so what this really describes is, like, this describes formal Laurent series which converge on the set of points x, the set of points which belong to, so really we should be thinking of these as functions on kind of this formal mirror for which the valuation of x falls inside P. And this is basically saying, like, this thing is basically saying, for each monomial we take its supernorm. Okay, so hopefully this makes some sense. Okay, so this is so basically we're looking at things which so the mirror as kind of, sorry, the symplectic homology is basically, in this case, it's basically analytic functions on the formal non-Archimedean mirror to the cotangent bundle of the torus. And then, so this describes what we associate to a polygon P. And then if we have we associate a polygon to a polygon Q, it's really just restriction. So kind of restriction maps, like Fleur theoretic, like the restriction maps of SH, or maybe let me say it like this: the maps from SH star of pi to the -1 P to pi to the -1 of Q are the obvious restriction. Okay, and maybe, okay, so this describes, and then there's just one more item, but before I go to the next item, maybe I stop, maybe is, any questions? What? The distance, so I say I kind of arbitrarily picked a point, as which I will take as my center, and then I'm saying that I want to describe, so you give me a monomial, like you give me an element of this algebra, I want to say it's norm. Or you give me a generator of this algebra as a vector space, and I want to describe its norm. So basically you gave me this z to the I. So I'm saying this I, you should think of it as defining some, like it's kind of a vector in an integral vector. So it defines kind of, defines some kind of, like in this two-dimensional case, it defines some kind of line, or kind of a family of parallel lines. They look at kind of what is the rightmost line. Like if I goes in this direction, what is the farthest I can go while still touching this domain? And that defines for me, okay. Okay, so I've described to you what is kind of the, like I said, it's a Banach BV algebra. So I've described you as the Banach part, what is the algebra part, and then also what are the restriction maps. And then the BV structure, very briefly, I will say, so what is the BV structure? It's also kind of important for the story. So the BV structure is kind of, so the BV operator is some operator to the exterior derivative. So you have kind of dual to this exterior derivative on kind of on the de Rham complex of basically, in this case, it's going to be SH0 under the isomorphism defined by omega equals dz1 wedge dzn z1 times zn. So maybe this is a little complicated sentence. So what I'm saying is you have some kind of algebra. It has kind of, we've described explicit generators. So you think of this algebra, you can associate with these generators, you can also describe an n form. And this n form defines a duality between polyvector fields and differential forms. And then you use this duality to kind of, you use the exterior form defined on differential forms and this duality to pull back an operation on this algebra of polyvector fields. And I'm telling you that this is the operation, which is the BV structure. Okay, yeah, so I think it took longer. I'll have to shorten the motivational part significantly. So yeah, so first of all, are there any questions? Okay, so I will just say one sentence about, okay, so now I want to say relative SH, mirror construction. So let me just say two things. So first of all, somehow, kind of, people who are familiar with symplectic homology know about some kind of categorical interpretation of symplectic homology in terms of, in abstract terms, it's kind of in terms of Hochschild cohomology of the Fukaya category. But so to make a long story short, kind of, I would just say mirror symmetry heuristics tell us that we should expect that if the mirror is smooth, at least, then so say we have some construction of the mirror, say we have some like an angel told us what the mirror is, and if it's smooth, then and then kind of a then sorry, SH0, let's just focus on this one. So the zero symplectic homology of subsets of the form like this, where pi, so in the background we have some SYZ fibration. So then this thing is the algebra of analytic functions on the mirror dual. Okay, so there's some heuristic which tells us that this should be, and then so now we can do some kind of reverse engineering. So suppose this is kind of if an angel told us what is M check. Now let's say we don't really know how to do mirror symmetry, then we can just apply this to reverse engineer and say that the mirror must be given as the union over, well, let me say small enough polygons. So the union over small enough polygons of spec of 0 of pi to the -1 of p modulo kind of the equivalence relation which arises from the fact, I mean, we have some kind of, we have a pre-sheaf, so it's kind of a diagram. So this induces some gluing, some gluing. of these spaces. Okay, so this should be the mirror. Okay, and this is the suggestion for what is the relative SH mirror. Okay, but of course one has to kind of, if one doesn't know that one started out from something which is actually a smooth manifold, it's not a priori clear that this is a smooth manifold. So that's something I want to say about in a second. But first, let me just kind of maybe let you absorb this or ask me kind of, does this argument make sense? Or
is the equivalence relation like what type of sets are you doing?
So yes, so basically, so think maybe a K3 surface, and then we have a cover, and I'm requiring that we look at small enough polygons, and the polygons should be kind of convex and so on. And then the equivalence relation is, well, I'm taking spec of this, and I'm taking spec of this. But on the other hand, I have I said there are restriction maps. So there's a restriction map from the white one to the small one, and from the red one to the small one. So this kind of introduces some kind of gluing relation in the reverse direction. And we basically require that these things are glued accordingly. Okay, so that's, yes.
Why did the first sentence tell us to that this is what we can do?
So it's like if the mirror is smooth, then this thing will reproduce the mirror, because this is set like, well, okay, maybe I skipped some kind of step. Like it's smooth, and then you expect. Maybe you should say a little more than just saying that it's smooth. Like what you expect from mirror symmetry is not just that it's smooth, but somehow that like there's a dual fibration, kind of pi check, from M check to B, and for small enough polygons, it is given as like these algebra. You can reconstruct the piece which lies over the small enough polygon from the functions. Okay? So it's, another way of saying it is that this kind of vibration is Stein. It has some kind of Stein property. But yes, I definitely should have said that. Okay.
P has a singularity in the time.
It's also like same thing. So
That's kind of the main.
Yeah, it is.
First takeaway. The construction, you can just write exactly the same spec as in 0 blah blah blah. Whatever P is on the base is the first thing to realize in this approach.
yeah. So yeah. So I have very little time. So let me just say kind of. But it's like if you start from a sheaf of, like basically we have a pre-sheaf, but we can say it's a sheaf. Like Umut's thesis showed, like for this kind of set, we know that it's a sheaf. I don't know if that helps us, brings us very far. If you start with a sheaf of BV algebras and you do this construction, it's not a priori clear that you get anything reasonable. Because for example, this relation I described is not necessarily an equivalence relation. You can look at the relation generated by it, but then you get something which is not well behaved in any way. So let me just say kind of what we like. Yes.
I have a quick question. Maybe it's a bit dumb, but once you do this like a gluing like process, right? Is it gluing just in the topological level, or it's a gluing of the complex manifolds or like algebraic varieties?
Okay, Umut wants to answer this.
Well, it's gluing of, in this case, you want to glue rigid dynamic spaces. So like take the definition of rigid dynamic space. These are all ethenoid domains. You have to prove this, of course. In the K3 case, for example, so the ideal case, these specs are all like this. SA zeros are all ethenoid. You can take their spectrum in any way you want, max spectrum or macro spectrum, and get some kind of ethenoid space, which is a rigid dynamic space, and then you can do rigid dynamic spaces. But you have to show many things, and you have to show that the prediction maps give you kind of analytic subdomain, and so on.
Yeah, so this is what I want kind of, yeah, this is the next thing I was going to formulate. Yeah, very
These
little
are
time.
all properties.
Yes,
You claim that these properties hold, which you are going to claim now.
yes, yes. Yeah,
Then you have to prove them. That's
Yeah.
the difficult part.
Yeah.
You
yeah,
have to prove properties.
yeah. So I guess, yeah. Okay, so yeah, so the basic question is when is it the case you start with some sheaf of algebras? When does this give you kind of a smooth manifold, which kind of looks like this, kind of pi check, like something with a smooth manifold, with kind of an SYZ fibration and so on. And I say smooth manifold, I mean a rigid analytic manifold. So okay, when does this? Okay, so when does this happen? So I will just formulate some sufficient conditions. And I think we need to verify three things. So one is that for P small enough, where's the other chalk? Here, okay. So for P small enough, we want SH0. So it's affinoid of kind of the right smooth of kind of the right dimension F. And if you've never run into like affinoid just means essentially it's kind of some kind of completion of an affine is one way maybe of thinking of it. So you should just think of some so analytic functions on some kind of open set in an affine variety, or maybe a compact set in affine variety. Okay, so this is so we want that this is the right type of algebra, and then we want the restriction maps. We want the restriction maps. So these restriction maps, you want them to be when you have kind of an inclusion of polygons, you want these restriction maps to just be kind of restriction to an open subdomain. And then there's something, well, one way would be to say some kind of co-cycle condition, but I think like the shortest way to say this is that it comes with an SYZ fibration, or kind of that there exists okay, so 3 is that there exists a function pi check from M check P. I will kind of we're epic. I'm just kind of this is kind of a shorthand for spec of SH0 of pi to the -1 of P. So we want a map from this to P such that these inclusions such that pi check to the -1. I guess this is what I want. Oh, sorry, I got confused here. say this. So this inclusion, this inclusion is the dual to these restrictions to these restriction maps is given by inclusions of subsets which come from functions. So for example, yes, so let me just, it kind of is dual, is the dual to SH0 to the restriction map. Or maybe, yeah, maybe I should have just said kind of this pre-sheaf is the push forward of, in other words, what I want to say is that, so if you, the pre-sheaf, which takes Q goes to this M Q, so this is the pre-sheaf, is, so there is some function such as this is the push forward of, sorry. I got it. I think I managed to confuse myself here with the exact problem. So I think, well, let me not try to be far. I think this says what I mean. But like the point is, let me not try to resolve. Like the point is that if you have, so one thing you want to know is that if you have kind of two separate polygons, then if you just have some arbitrary algebras, it's not even clear that when you do this dual thing, that like these two things are even disjoint. So this condition tells you, for example, that the sets which are associated with disjoint polygons are disjoint. Now, okay, I'm running out of time. And just one thing which is not kind of to answer that it's a mirror. It suffices like to conclude that you have a manifold, it suffices to have these three conditions. And then you also want, for it to be a mirror, you also want some global Calabi-Yau form. So, okay. Which is not related to the problem of having of this thing defining a manifold, but it is kind of, you need it for mirror symmetry. Now, okay, so what can I do in, like, what do I have? I have like 11 minutes. Yeah, so let me just say, so, oh, okay, so what I'll say is what goes in, like, so I'm claiming that under broad, so there are two things. First, like under broad circumstances, relative SH can gives you the favorable answers to these questions. And in particular, one can kind of completely work it out in the case of Lurey-Jenga interiors. So let me, okay, so what I'll say is kind of what are the problems that one needs to overcome, and then very briefly how one overcomes them. So there are two problems to overcome. Like I've written down a list of properties that we need. To overcome them, so there are two, there's a local problem and there's a global problem. So the local problem okay. So cover B by polygons P such that kind of if you take such that for for K, which is, let me even say PI, just to have an index in the story. So for one of these polygons, such as for K, if we look at the local story, if we look at kind of, as presumably this is a Liouville domain, which we're thinking of something which maybe contains some singular point. This was the, like what as Philip asked. We want kind of the local story satisfies 1 through 4. Okay, so it comes equipped with all these things, and then 2 is the global problem, which is show that SH of kind of, if you look, so this is kind of the undeformed local story. Then you want to look at this local thing inside some ambient space, and then show that this is a trivial deformation. This is roughly what you need in order to solve the problem. Now, what I can do in the time that I have left, so on Friday, I gave a talk about how one uses kind of family FLIR to construct the mirror to the regular fibers. And it was kind of a pretty complicated story. So I think I can show you maybe that easily how relative SH gives a solution to the same problem. Of course, the point of relative SH is that it also gives a problem with the singular fibers, but I don't have time. That much time I don't have. So what can I say? So first of all, consider relative S. So now let's focus on a particular case. And the particular case is going to be, okay, so first of all, a general remark. Observe. Yes. What? Yes, I keep it. Okay. So let's make the following observation. So I've written already on the board what is the story for the local for regular fibers. Observe if P contains no singular values of the fibration, so it's kind of a regular fiber, then 1 through 4 hold, because that's what I spent some time kind of describe to you. What is the local algebra for a polygon which contains no singularities? So basically, so it remains to solve the global problem. And here's what, and this we can do. This is a paper that Umut and I have written last summer, and how is it resolved? So let me say, so consider one of these Lurijenga interiors. So I should describe what is the symplectic form. So I will be very brief. So there's a symplectic form such that kind of we think of it as so it's going to be M, and it's so there's going to be some Lurijenga interior, and it has a map to R2. Which has kind of an integral affine structure, which is obtained from something called an eigenray diagram. I don't know if, was this discussed? So what we're thinking of is we have a Lagrangian torus fibration over R2. We have some finite number of nodal singularities. Each of these nodal singularities, the monodrome is of course 1, 0, 1, 1, and kind of the way this integral affine structure is obtained is really by kind of taking R2 and doing some branch cuts in R2 along these tails. So this is a particular type of Lagrangian interior with a Lagrangian torus federation. So now, so there are two theorems in here. So theorem 1 says. So let me just introduce. So we have kind of this focus singularity. Then so let's look over one of these points here. So then we have a focus singularity, and so a definition, a Lagrangian tail is kind of a Lagrangian disk, which emanates from the nodal point and projects kind of it's a Lagrangian disk projecting onto a ray, like one of those monodromy invariant rays, and then so theorem for each p in kind of each focus point, pick a Lagrangian tail LP such that for simplicity I will just say something more limited than usual. So such that say LP are just disjoint if P, so they're pairwise disjoint, though we don't usually need this. Then we have then if we look at N and we remove these Lagrangian disks, then we get something which is symplectomorphic to the cotangent bundle of T2. Okay. Now, what does this thing bias? So this is some kind of statement, like you have some kind of symplectic manifold, you have a Lagrangian torus federation, you remove some Lagrangian disks, and then you get some familiar symplectic manifold. Okay. Now, what does this bias? For this, I have to say the second theorem, which says in such a situation, the deformation is trivial. So there's locality theorem. I won't formulate it. So again, this is from last year. So let's call this manifold Y. So in this situation where you have kind of an entire manifold inside another manifold, then I will try to explain what I mean by this situation, but let me first, in this situation, the deformation is trivial, meaning the symplectic cohomology of, so if we have some polygon in here, and the symplectic cohomology of this thing relative to Y, which is just kind of T star T2, which is and relative to the submanifold we get after removing Lagrangian disks, is canonically isomorphic to the symplectic cohomology of in relative to the ambient space. So this basically says that the second property that we want, that we get a trivial transformation, holds for polygons which lie in the complement of these tails. Then we can do an operation which is, now note, we can modify pi by nodal slides, meaning we can move these singular values along these rays, and we can kind of and we can pick opposite tails. So basically, we can so we could kind of we have this particular presentation, but if we can then modify the presentation by taking the opposite ray, and if somehow it hits one of the other rays, then we can slide it away so that we. So basically, this tells us that we can cover our manifold with different kind of copies of kind of the torus inside Y. So you get different identifications, kind of you get different embeddings. So what do you get? You get different embeddings of E star T2, which cover the complement of the singular points. So this tells you essentially, and maybe I need to add. So this tells you that this gives you the mirror over. And unfortunately, I have to stop here, but maybe somebody will ask me a question about instanton corrections, and then I will be able to just complete what I want to say.
Stop.
Yes, okay. So this gives the mirror for the regular fibers. Okay. Yes.
Okay, let's thank you out. Any questions from the room? So you have this 1 to 4 that we were looking at.
Yes.
So the mirroring constructor was this identifying object with like a gallery of 1 to 4 satisfied. Is it like obvious that you get a gigantic source separations with the relation of the constructor?
So you're asking, will I have this, like one of the things that I said 1, 2, 3, 4, and one of the things was pi check. You're asking, will I get this pi check? So yeah, so this comes. So yes, the answer is yes. You will get pi. You will get. So the point is for each. So this is kind of came out. So pi. So for the regular fibers, recall I wrote down to you what is kind of what is relative SH for such a. What is kind of the local story of relative SH, and it comes with, I guess I never wrote down what is pi check. So pi check is the thing I wrote last week, which is the valuation map, right? So pi check, well, you have this kind of,
the constant
something like that, yeah. So it goes to this map. Yeah, you're right, thanks for it. So it just takes, yes. So this you get for one element of the cover, and the point is when you kind of go past to another cover, it's still compatible. So yes, you get some kind of, so you do get a function like that. No, I'm saying there should be some distinguished Calabi-Yau form. Yeah, and that's also a feature that you have here, but I think. So locally, there's a distinguished Calabi-Yau form, but one has to show that these locality maps kind of, when you cover them, and like when you cover them by different maps, that it's kind of compatible. But that's also a feature.
And in this case, that form will get around with standard form of K-star.
What?
This would turn out to be the standard form of K-star that you're supposed to somehow do together.
Yes.
Other questions?
Question about irregular or non-regular fibers.
Mhm.
Like essentially, Yeah, so maybe you can cover everything by polygons except for these singular binaries. So like, does that already then have the correct analytic structure?
Yes.
Like what you, and then
Yeah.
you flew in, like, for a small neighborhood of
You need to, you can't just use that local model. You also need to use the local model with one singularity.
Yes, but he's asking if we take, does this thing, is this kind of, this is the instant uncorrected mirror, like, if you take the correct mirror, then you restrict to the complement of the, restrict to this opposite, so this already has all the instant uncorrected.
So it already has all.
Yes.
And then you just need to glue it to the standard model.
Yeah, it's not, I need to glue in, like, I've
The
kind of,
fact that you can't glue in something is a not trivial thing.
yeah,
You need to have constructed the rest of the information.
yes, like, that's like, the whole point is like, if you just take some, like, you can always, like, there's a naive mirror, which, the semi-flat mirror, but that you cannot extend.
Sure. But I guess I'm asking, like, you maybe have some algebra that you get for like a small polygon around a singularity, right? And does this machinery still gives like
Yes.
restriction map to a sub polygon?
Yes,
Singularity
yeah.
and that includes,
Yeah,
So that's also part of the complex. When we actually do the construction of the mirror, we use those directly as well.
I see.
yeah,
But to compute those and to compute the corresponding restriction maps,
It's hard.
it's a difficult thing.
yeah, but basically the
This approach is that you don't have to correct. Like you can just build the complement
Yeah.
using this technique.
it's not we build a comment, we build out, like, we just, like, I wrote down a formula for the mirror, and we just proved that thing that we wrote down, that it really is a smooth manifold. That's not some,
Yeah, some things that are super obvious, if you think S by Z terms become like very complicated in this. Like there's really a trade-off of kind of what easy and what hard. Like this, I mean, this jointness property, for example, like it's still to me kind of a mysterious thing. Like you have to big polygon, small polygon, which are disjointed, and if you do this kind of echelon domain construction, you get two echelon subdomains, and they somehow don't intersect. And you can check this is true, but I don't know what it means symplectically. If you think of it as a tool, as far as department, that's something that you take for granted. It's automatic, there's nothing to it.
yeah.
But here it's a property somehow, like, and I don't know.
Yeah, because we don't start with describing as a set of points and construct on it a structure. We start by a set of sets.
Yeah, it was active when they had strict moderator
And now,
mask it all.
yes,
Okay,
yeah,
so more
yeah.
questions.
yes.
I was comparing that buttons, which is like, I mean, it kind of feels like when you define like a scheme and you require that morphisms be local morphisms of local grids, so you kind of know where a point actually goes. So like, is there some version of this thing where you do a point for your compact set that like
I'm saying you can kind of construct it by doing it formal input or something.
I don't know, just well, no, yeah, I'm not sure, but like maybe you could, I don't know, maybe there's some condition, you can express this condition in terms of just like an inclusion of a point in some other context set. But
Yes, so
Well, I'm not sure I understand.
I understand it's one thing, I don't know if that's what you meant, but you need to, it is possible to interpret the points of the space that you constructed. But I think it depends, there are various levels of which point, right? Is it the point of the backwards space or is it the point of the rigid analytic space? So I think if you could interpret the point of the backwards space, that would be great. But I don't think we have that.
Are you saying interpret them as symplectic?
Yeah, some kind of symplectic thing. But
Well, you could say they are multiplicative semi-norms.
That's a family blur.
Mhm.
But the family blur here is supposed to be just like at least as an almost subset and this thing.
Yeah,
those
so-
are the points, like the driving.
I mean, if you say, no, isn't it supposed to just bijection? Ah, you're saying like if you do the family FLIR together with the like, there's these new things. I don't know where it stands. Yeah. But at least if we restrict to the regular fibers, then they're just in bijection. Like this should automatically be the instant-on corrected thing. And nobody asked me how instant-on corrections occur, so you won't know.
So, but this sort of condition, just, this condition was essentially that like the map of the inclusion of algebras is kind of induced by a map of the skeleton in some an inclusion of the skeleton.
And induced by the inclusion of polygons in the base.
It's polytones.
Yes.
Yeah.
It's not skeleton. Yeah, but
Yeah.
But there's it doesn't exist. Like you just have the abstract algebra, they don't count with a map like to the base. There is a map to the base, and we
Well,
expect there is some way that.
But spec, like, yeah. Like if you just have algebras, then the spec of these algebras doesn't have a map to the base. Like you have a sheaf of algebras, you don't get a space together with a map. So you need the.
We can continue later, so let's see if there are any other questions.
There are two more questions, so I will ask very quickly.
Okay,
So you do the construct your mirror using SH0.
Right.
So what happens to the rest of it?
so the rest of the part, they correspond kind of to polyvector fields. So they have a role, for example, if one wants to relate kind of enumerative mirror symmetry. So this, one of the advantages of this approach is, at least we expect that there should be some kind of nice conceptual direct proof of enumerative mirror symmetry.
May I ask a question?
Yes.
So did I understand correctly that this approach, at the moment at least, or let me start differently. So this relative symplectic homology seems extremely general, right? So you can define it for, it's just there, right? So you could in principle do the construction, but then you listed these 1 to 4. And did I understand correctly that at the moment you do need kind of explicit control of the singularities of your SYZ fibration to make this work?
Okay, that's a good question. So in my unrealistic preparation for this talk, I was actually going to talk about this in the kind of the overview part. So yeah, maybe in the 5th hour. So basically there are two, like there is like kind of this project that Umut and I are doing is kind of, I think the generality where you can push it is, yes, kind of like this applies to roughly, I think, to local Abiyahu historic models, and it has to do exactly with where you have controls.
With this particular form, not with I don't think it even applies to this kind of finite volume restriction of Taylor form from the magnification. Just this imaginary part of
well, I don't know if I wouldn't characterize it like that because like I don't know exactly what the characterization higher dimension, but and this has in 2 dimensions it's that, and we can push this to a large subclass, I think, of kind of local Abiyahu historic models and there we use kind of explicit control, but that's not like. There's also kind of ongoing work, like both me and Umut, I think, is also. Okay, so I have some work in progress, which hopefully will come out, which kind of deduces 1 through 4, kind of in more kind of by. Yes, you always need to make some assumptions, but not by saying like here's a list of models for which we compute things, but by kind of listing some properties such as kind of being torsion-free and so on. So I hope very soon I will have like at least the first paper in the list out. And yeah, so the aim is really to also be able to prove these properties abstractly without kind of first computing what the model is. Does that?
Well, but you have to put in some kind of space where your P lives, right? You need some kind of base of the SYZ.
Yes. This is for SYZ fibrations. I don't know.
But it doesn't SYZ fibration. You don't have to like it could, we could have some coarser information than an SYZ fibration. Like in the end, you will cover with some polygons, and you only kind of care what happens at the boundaries of the polygons.
Yes.
Inside the polygons, you don't need
exactly
the structure of the fibration.
So I have trouble understanding what you're saying. The audio is not very good for
What Omot is saying, like, is that we need some kind of very weak notion of SYZ federation, or maybe something which should not even be called SYZ federation, because what we want is to be able to cover our manifold with polygons.
Right.
We want some kind of Lagrangian torus federation near the boundary, but inside maybe we could have some open set where we don't even have a Lagrangian torus federation. So
I see. So this, I mean, Yush and Lin had these kind of things where they construct on this kind of special Lagrangian tori close to a divisor or something. Would that kind of be a setup that presumably that could work? If you just know one good torus, one Lagrangian torus, okay, and then with some properties, and then you're saying, hey, this might be enough to define something.
I think it could be. Like you have to know that all the special Lagrangians are placed in kind of a nice way so that they actually give you a cover, and the boundaries intersect in kind of a nice way so that you have a shape property. They can be arbitrarily placed special Lagrangians, but if they kind of cover the manifold or something.
I see.
Yeah. So like one of the things I was going to say is there is the question of what does differential, like there needs to be input kind of from Schlur theory to say what kind of weakening of the notion of Lagrangian torus federation we need, and then there needs to be input from differential geometry to say what kind of weak notion of Lagrangian torus federation we actually get. And so there should be some feedback between these two, and it's not happening enough. So for example, Yang Li, I think he constructs things, but because he says nothing about the singularities, I don't know how to use it. So I would say it's an open problem. What is exactly the extent to which you can apply this? But definitely it applies in much larger generality than just giving some list of singularities for which we know how to compute things.
Okay, thank you.
Other questions?
There is a question here from Zane Nicolas. Is the relative SH known for a neighborhood of the non torus?
Yes. Like that was supposed to be the 6th hour of the talk.
But hopefully this paper will come out soon. Yeah, I mean it's almost finished, but I always underestimate how long it will take, so I don't want to give an estimation. But I want to say next month. That's what I want to say.
Yeah.
It's a completion of the, it's like you know what the SH of the complete neighborhood is. So it's a completion of that. That question is not that difficult. The difficult question is to compute the restriction map to polygons which don't contain the singularity.
Yes, that's.
I answered that. Sorry.
But no, thanks. No, it's good. It's good.
Yoel Groman asks, what would be the complex pressure of the mirror? Probably he has to bring the top and the center, right?
What will be like we construct a rigid analytic manifold. Yeah, that's
Yes. Yeah, it's a good question.
Okay, so let's thank you out.